All right, so I wanted you to come up with a relationship between the force you're applying and the mass. And most of you did a really good job of coming up with a graph that had the quantity of what? What did we put on this vertical axis? Force. And what quantity did we put on the horizontal axis? The mass. And you guys measured it in grams, and that was perfectly fine. Okay? All right. So when you graphed this, and I get to make these look real pretty, but you had maybe some points that look like that, and then maybe you had some points that look like this, and then that gave you a best fit line like that, and a best fit line like this, where the high slope one was the one that was not moving, right? Or it should have been for most of you. And then the lower slope was when it was moving. Okay? So let's draw a let's look at, what is the equation? You guys did a good job of drawing the force. And this was the applied force. The applied force. This is what you are applying to the object. And then you got some slope number, and I'm going to write the word slope because the symbol you use in math for slope is m. Right? What does m mean in physics? Mass. So that's going to get really jacked up. So let's just, I'm going to use the word slope right there, and then what's on the x-axis? Mass is on the x-axis. And then some of you had a slight intercept or a significant intercept, but that just goes back to your experimental error. Okay, so we had the force applied is equal to the sum slope number times m. Now let's look at the free body diagram. Remember yesterday we talked about free body diagrams of the object when it's not moving. What's a fancy science word for not moving? I heard it, static. Static. That is the fancy word for not moving. Okay, when we draw a free body diagram, we draw something like a circle or a square or a dot to represent the object. And then we're going to draw the interactions with that object. So, think about all the things that are interacting with our block. The Earth's interaction would be which way? Down. And you guys yesterday were drawing those arrows. And let's call that the force due to the Earth, the force of gravity. Okay? And then I also heard friction. Well, what's that the interaction between? The block and the surface, right? The block and the wooden surface it was on. And which way would friction point? If you're pulling it to the right, which way would the friction point? To the left. And now I'm going to make, so this is the force of friction static. And I'm going to put a little S there. So I love some subscripts. What else was interacting with our block? You were pulling on it, right? Did you apply a force? Yeah, you sure did. And you were pulling it to the right. So just call it the force due to you, or the force that you applied. How about that? Force applied. Is there anything else that was acting on this this block? So far we've got that you applied a force to the right. That was your interaction. The surface was applying a friction force back on the object. The Earth was applying a force down on the object. What do you think? So the table applies a force. Oh, and that is up. Okay. Now we call that force, you can call it the parallel force. Pardon me, the perpendicular force. You can call it the table force, whatever you want to call it. But we steal a word from math, normal. Do you remember in math class, a normal line is perpendicular to another line? They're normal to each other. So it's a math word, but we have the normal force. Okay, so let's do what we did yesterday, and let's sum these forces. Now, yesterday we only had vertical forces. Today we have vertical and horizontal forces. So we have forces in the x direction, and we have forces in the y direction. So look at the x forces first. This is when you were pulling on the object, but it wasn't going anywhere. What was its acceleration? 0. It was no acceleration. Okay? Now, I haven't drawn these to scale or anything. So, how should these two arrows, the force applied and the static force of friction, how should those two arrows be size-wise? The same, because it's in what? It's in equilibrium. So if I sum the forces, we have our force applied, and because it's to the right, I'm assuming there's a positive there, minus our force of friction static. And if I add those two equal forces together, but one is positive and one is negative, what do I get? 0. And this is because it's in equilibrium. Equilibrium. All right, now let's look at the vertical forces. I'm just going to scoot up just a little bit there. The forces in the y direction. What do you think size-wise for this normal force and this weight force, the force of gravity? They should be in equilibrium as well. The normal force is up, so make that one positive. The gravitational force is down, so make that one negative, and they should add up to 0. Beautiful. All right, so now what I've done is I have created two force equations for this situation. That means if you take this equation here, the force applied has to be equal to the static friction force, the maximum static friction force. Because didn't the force get bigger and bigger and bigger until it was too much and it couldn't handle it anymore? So that was our maximum. And then also, isn't the normal force equal to the weight? If I rearrange those two equations. All right, so let's go back to your graph. From your graph, you had that the force applied was equal to the slope value times mass. Okay? Now the force applied is also equal to the force of our static friction. And this is still our maximum static friction. Okay? Slope. Now static friction is the interaction between the block and the surface. Which one of these forces, force applied, force of static friction, we've already covered that one, normal force or the gravitational force, which one of those forces is between the block and the surface? Which of those forces? The four forces that are acting on the object. The normal force is also between the surface and the object. Now, yesterday, the gravitational force we defined as being equal to m times g, right, from yesterday? Okay, so what if, for the force of static friction, because this is between the surface and the block, so slope times m, if I multiply this by g, that's going to change this slope. So the slope will be a little bit different. It'll change the slope value because all I've done basically is multiply the x value by 10. So if I do that, I'll have m times g, which is equal to, if I go all the way back through here, the normal force. So then I can write, so now I have an equation that's about the interaction between the surface in the block and the surface of the block. And then I still have this slope value that I need to define. Well, that number is specific for every different object, every different surface-surface interaction, and we call that the coefficient of friction. And the symbol for that is a mu. It's kind of like an M and kind of like a U, and I'm saying mu. All right, so that means that our equation for the force of static friction, and I'm going to put a little max down here just to remind you, would be equal to mu static times the normal force. And that is your you like to put boxes around it. So there's the equation for the maximum static friction force. So let's talk about units for a second. Force is measured in newtons, and that would be equal to something times normal force is measured in newtons. So what do you think this thing has to be measured in? If I need newtons and newtons on both sides? Nothing. Okay? The static coefficient is unitless. It's a number. It's always a number between 0 and 1. So you won't have any negative coefficients of friction, and you won't have any that are over 1. If you do happen to mathematically calculate something that's negative or over 1, then that gives you an indication that you've probably done something wrong. Or if it's a situation where you're trying to determine, is it possible for the object to move, and you get a coefficient of friction of 1 or greater, then it's not possible for the object to move. Okay? But if you have a coefficient of friction of 1 or better, it's like stuck. Somebody has glued that object down. It is super sticky. Okay? All right. So now let's look at the other case. It wasn't static. It was, what word would be opposite of static? Kinetic. Kinetic or moving. Kinetic's the fancy word. So in our kinetic situation, let's draw a free body diagram. So here's our little object. What was interacting with the block as you drug it to the right at a constant rate? What did we mean by constant rate? Same what? Same force, okay. So at a constant rate, what wasn't changing? The velocity wasn't changing, so what was the acceleration then? 0, perfect. So we had a constant velocity and a 0 acceleration. Okay? What was interacting with our block that we were pulling at a constant rate? What was interacting with the block? The person pulling it. So we have a force applied. Which way? To the right? What else was acting on our block? Francesca? Yeah, which way would the force be? To the left. Now, instead of static friction, though, it is a force of friction, but it is kinetic. So I'm going to put a little K there. I don't know. We're going to see. So what else was interacting with our block? The earth was interacting. I heard somebody say gravity. We're going to say the earth was interacting, and it was applying a gravitational force. What else was interacting with our block? The table surface, and what was it doing? Pushing it up. That's right. And what did we call that upward force? The force normal. So the normal force is perpendicular to the surface. The gravitational force is straight down. Friction force is a resistant force between the surfaces. So the acceleration is 0 in this case. Now if we scroll way back up here and look at this case where it was static, the acceleration was 0 and it's in equilibrium. Okay? Now if we go pop back over to a couple of days ago where we had an object that was hanging right there, was it in equilibrium when the tennis ball was hanging in the front of the room? Yes. And what was the acceleration? 0. So acceleration equals 0 and it's in equilibrium. Those two things have gone together twice already. So now our object moving at a constant speed. Alright, so when an object is moving at a constant velocity, the acceleration is 0. Just like in any of the other cases where acceleration was 0, it's still in equilibrium. It's still in equilibrium. So that means that when I sum the forces in the x direction, the forward force, the applied force that you pulled on the block with, minus, because this kinetic friction force is to the left, will have to equal 0. So these two vectors are the same size. Those two vectors are the same size. It's not accelerating. Now for the moment when you grabbed the spring scale and you were pulling it to the right and it wasn't moving, and then there was a moment where it slipped and started moving, that situation was unbalanced, disequilibrium, non-equilibrium, and it accelerated. But once you got it going and then you adjusted the spring scale so that the force was measuring about the same number the whole time you were pulling it, the forward force and the back force, the friction force, were equal to each other. Okay? It's when you increase that forward force that it would accelerate and they would be unbalanced. Or when you decrease that forward force and the friction force stays the same and it decreases and decreases and the object slows down. That's what happens when you slow down in a car. You disengage the engine and you start the brakes and you're causing friction and no forward force and you slow the object down. It's an unbalanced situation. So when we're moving at a constant velocity, we're still in equilibrium. So that means that the sum of the forces in the y direction, and you guys told me that the up force, the force from the table, the one we called the normal force, was balancing the gravitational force, and the normal force is positive, so there's an understood positive right there. The gravitational force is pointing down, so that negative takes care of that direction. You sum them up and you get 0. So if I look at these two equations for the forces, if I go here, let me grab this, I'm just going to write this down here, I like arrows. So wouldn't the applied force be equal to the force of kinetic friction? If I rearrange this equation right there. And what about this guy right here? If I were to rearrange him, wouldn't the normal force equal the weight or the gravitational force? So yesterday on your graph, you came up with an equation that was like the force applied was equal to a slope times mass. Is that right? So now, look, I can make a substitution. Boom. If the force applied is the kinetic friction force, then I can make an equivalent substitution there. Times our slope value. All right. Now, mass, m. Is there anything wrong with multiplying by g and dividing by g right there? Now, F of force of gravity, F of g, we determined that equation a couple of days ago. What's the gravitational force equation? Do you remember? F of g equals mg, exactly. So now, look, that means if mg equals F of g, which F of g equals the normal force, can I stick this guy in right there? I'm just making substitutions into the equation that you created. So now I get the force of kinetic friction is equal to whatever your slope value was divided by g times the normal force. Now this value right here is constant for the surface to surface interaction. This right here is the coefficient of kinetic friction. And we use that symbol mu. So mu k. So your force of kinetic friction is... Alright, so what I get then is a final equation for the force of kinetic friction. So this is your kinetic friction force. Let me scroll up. And this is your coefficient of kinetic friction. This is your normal force. And unit-wise, force is a force, of course. So this is a Newton, and this is a Newton. And when you have a Newton is equal to something times a Newton, what's the something? Nothing. No thing. Oh, that's silly. But nothing. No unit. It's just a number. Now, let's talk about that number. We looked at our graph from yesterday, and we had a steep slope and a shallow slope for the two different interactions. So we had one that was a high slope, one that was a lower slope. This was the force applied, which we have learned is now the force of friction. And if you convert this to weight, so you had mass, if we convert those to weights, which would just be moving a decimal, we could have the gravitational force here, and that would be in newtons, and this would be in newtons, and we get these slopes. So the slope of this graph right here would be your coefficient of static friction, and the slope here would be the coefficient of kinetic friction. And as a rule, the coefficient of static friction is always greater than the coefficient of kinetic friction. It's always harder to get something going than to keep it going. Another important thing about the coefficient of friction, if we did enough experiments, you would learn, all of you got a number that was positive, okay, but you all got numbers that were less than 1, most of you. I think there might have been one table that had some problems with their numbers, but most people got like 0.005, 0.0065, 0.007. Okay, so your coefficient of friction is always going to be positive, but it will be less than 1. And then your coefficient is going to kind of determine a relative roughness or smoothness, depending on how you want to look at it. So like a 0.9 is rough compared to a 0.2. Does that make sense? A 0.9 would be a very high slope and a very rough surface. A 0.2, comparatively, would be a smoother surface, a lower slope. And you know, I love a graph, so this is a graph of force versus force. Now, in all of these cases, there was a theme that I was trying to get you to understand, and that was what? What was the theme? All of these bodies were in what? Equilibrium. And equilibrium goes with what? What does equilibrium go with? A zero acceleration, which then gave us what? It also goes with what? What was the other thing? The sum of the forces was 0. So this is Newton's first law. So the object at rest stays at rest, and object in motion stays in motion unless acted on by an unbalanced force. In all of our cases, we had balanced forces. The objects were in equilibrium. So that's what equilibrium looks like. It looks like an object not moving. It looks like an object moving at a constant rate.